A graph is a collection of vertices and edges widely studied in mathematics. In graceful labelings, we label the vertices of a graph with a vertex labeling. Then for each edge, we take the absolute difference between the two vertex labels surrounding that edge to obtain the edge label. If the vertex labels are all unique and range from 0 to the number of edges, and the edge labels are all consecutive ranging from 1 to the number of edges, we can call this a graceful labeling. The graph shown has been labeled with a vertex labeling, which can be verified to be a graceful labeling. The vertex labels are unique and are all between 0 and 12, the number of edges. Taking the absolute differences to obtain edge labels, we can verify that the edge labels are consecutive, forming the set 1, 2 to 12.
Among the types of graph families that we considered in our project were trees and cycle chains. Trees are graphs with no loops, so that there is only one way to get from any vertex to another. Cycle chains are a series of adjacent cycles, which resemble regular polygons in graph form. One of the most famous unsolved problems in graph labeling is the graceful tree conjecture, a 36-year-old unsolved conjecture towards which we make significant contributions by proving a more inclusive infinite family of trees is graceful than has ever been shown before. Additionally, we prove that several infinite families of cycle chains, namely the snakes and diamondbacks, have graceful labelings as well.
Graceful labelings are the solutions to the optimal reference system problem in networks. They are very significant in related fields because they provide a way to label nodes and links between nodes with the lowest possible upper bound. Examples of where this labeling is useful is in social and communication networks, where nodes can represent users and edges, links between them. Our results on trees can speed up efficiency in these networks by allowing vertices and edges to be uniquely determined through subtraction in an optimal way. In addition, our research in cycle chains can be applied to the frequency assignment problem for radio networks. By denoting each radio cell as a set of connected vertices, our results provide an optimal reference to adjacent vertices and are directly applicable as models of networks resembling adjoint cycles.